Our story is a long one. It is written in stone, in bones, in the very code that makes us who we are. For billions of years, life on Earth has been transforming. Species rise, species adapt, species sometimes vanish. We humans are part of this grand, unfolding narrative. A recent chapter, but a powerful one. To see where we might go, we must look back at the forces that brought us here. This journey of change is called evolution, not a destination, a continuous process. It has shaped every living thing, from the smallest microbe to the largest whale, and it has shaped us. Evolution is simply change over time, life responding to challenges and opportunities. Think of it like a river carving a canyon. Water flows, slowly wearing away rock and creating new landscapes. In the same way, life flows through generations, slowly changing form. The changes are not planned, not directed toward a specific goal, just the result of a few fundamental principles at work. For humans, this took millions of years. It sculpted our hands to hold tools, our legs to walk upright, our brains to ask questions about the universe. The primary engine is natural selection, a beautifully simple, profoundly powerful idea. The world acts as a filter. It determines which traits are passed to the next generation. This process is not conscious or cruel, just a consequence of life's realities. Some individuals are born with traits that give a slight advantage, a little faster, a little stronger, better at finding food. Those small advantages add up, improving survival and chances of offspring. This is our story so far. Descendants of countless generations of survivors. Our ancestors faced ice ages, droughts, predators, diseases. In each generation, the best suited passed on their genes. This relentless filtering made us resilient and adaptable. It gave us intelligence to solve problems, social bonds to cooperate, curiosity to explore. But today, the rules of this ancient game are changing. Forces that shaped our past are now joined by new ones of our own making. Well, let's break down natural selection into its simplest parts. Imagine a population of animals, perhaps a herd of deer, living in a snowy forest. Within this herd, there is variation. Some deer have slightly thicker coats than others. Now, imagine a particularly long and cold winter. The deer with thinner coats might struggle to stay warm, get sick, or find it harder to search for food. The deer with thicker coats, however, are better equipped to handle the cold. They have a higher chance of surviving the winter and being healthy enough to have fawns in the spring. This is natural selection in action. The environment, the cold winter, selected for the trait of a thicker coat. The deer with this trait were more likely to survive and reproduce. Their offspring would inherit the genes for a thicker coat, making the next generation, on average, a little bit hairier. Over thousands of years, this process can lead to significant changes. The entire deer population might evolve to have much thicker fur, becoming perfectly adapted to its cold environment. The same principle applies to speed, vision, or any other trait that affects survival and reproduction. It is a slow, patient, and unguided process of adaptation. For early humans, the pressures were immense. A person with better eyesight might spot a predator from farther away. Someone with a stronger immune system might survive a deadly plague. An individual who was better at communicating could organize a more successful hunt. These individuals had a survival advantage. They lived longer and had more children, passing on the very traits that helped them succeed. This is how our brains grew larger, our social structures became more complex, and our ability to use tools became so refined. Natural selection was the sculptor, and the environment was its chisel. For most of human history, the rules of survival were set by the natural world. Today, those rules are being rewritten by technology. Our ingenuity has created a buffer between us and the raw forces of natural selection. Consider medicine. In the past, a child born with a severe genetic disorder or a weak heart might not have survived to adulthood. Nature, in its impartial way, would have filtered these genes out of the population. But now, with advanced surgery, medication, care, that child can live a long, healthy, and fulfilling life. They can grow up, have children of their own, and pass their genes on to the next generation. This is a wonderful achievement. It reflects our compassion and our desire to reduce suffering. We should celebrate our ability to save lives and improve well-being. However, from a purely biological perspective, this changes the evolutionary equation. Traits that might have once been disadvantageous are no longer being removed from the gene pool with the same frequency. The genetic makeup of the human population is changing in ways that would have been impossible a few centuries ago. Our culture of care and medical technology have become powerful evolutionary forces. They are preserving a wider range of genetic diversity than nature alone would have allowed. It is not just medicine. Our entire modern lifestyle is shaping us. Think about eyesight. In the past, sharp vision was critical for hunting and spotting danger. An individual with poor eyesight would have been at a significant disadvantage. Today we have eyeglasses, contact lenses. A person can have terrible vision but function perfectly well in society. There is no longer strong selective pressure against the genes that cause nearsightedness. The prevalence of nearsightedness has been increasing in many populations around the world. Our technology has made the trait less of a handicap, so it persists and spreads. The way we work, the food we eat, the social structures we build, all create new selective pressures while weakening old ones. For example, a world that values knowledge work and complex problem-solving may select for cognitive traits that thrive in information-rich environments. We have moved beyond simply influencing evolution indirectly. We are now on the cusp of directing it. For decades, we have known the instructions for building life are written in DNA. This is the book of life, a code of 4 chemical letters, the blueprint for every cell in our bodies. For a long time, we could only read this book. The Human Genome Project, completed in the early 2000s, was a monumental achievement. It gave us our first complete reading of the Human Instruction Manual and allowed us to identify specific genes linked to thousands of diseases and traits. This ability to read our own code was a revolution. It opened new possibilities for understanding and treating disease. Doctors could identify people at high risk for cancers or heart conditions and recommend prevention. Scientists could study the genetic roots of complex disorders, Alzheimer's, schizophrenia. It was like finally having a map to a vast and mysterious land. The dream of genetic engineering has been around for a long time. The idea is simple. If a disease is caused by a faulty gene, why not fix it? Fix. Replace. For many years, this was science fiction. The tools to edit DNA were clumsy, expensive, unreliable. You were more likely to destroy the book than to make a precise correction. Scientists made slow progress in simple organisms. Applying them to humans seemed distant and difficult. All of that changed. New tools made gene editing precise, cheap, easy to use, like a molecular word processor. We now possess the power not just to read our source code, but to rewrite it. This capability brings incredible promise. For the first time, we have a realistic path toward curing a vast number of genetic diseases. Conditions like cystic fibrosis, sickle cell anemia, Huntington's disease, caused by errors in a single gene. With CRISPR, we can envision correcting these errors directly in a patient's cells, providing a one-time, permanent cure rather than a lifetime of managing symptoms. Clinical trials are underway, and early results are showing incredible promise. This could alleviate an immeasurable amount of human suffering.
Human genetic editing is no longer science fiction. CRISPR cures are here. There are only 2 monogenic diseases caused by a single gene, that currently have a CRISPR-based treatment with regulatory approval in major markets. The first one is sickle cell disease. The second one is called transfusion-dependent beta thalassemia, a therapy called Casgevy. That's the CRISPR Cas9 you've probably heard about. It edits a patient's own blood stem cells so they start making a healthy form of hemoglobin. One-time treatment, designed to be curative for eligible patients, approved in the UK and the US starting in late 2023. That is a legit milestone, but here's the line you should draw in your brain. Cured with approval versus being tested. Approved list? It's those 2 blood disorders, both tied to mutations in the HBB gene. Everything else we are seeing about CRISPR is promising, exciting, sometimes jaw-dropping science, but it is still in clinical trials. This technology is expanding fast. Let's take a look at some examples that are currently in clinical trials. Hereditary transthyretin amyloidosis, in vivo CRISPR, to switch off the liver gene that makes the toxic protein. Early human data looks strong. Hereditary angioedema, single-dose CRISPR aimed at slashing sudden swelling attacks. Big reductions reported in trials. Leber congenital amaurosis, certain inherited blindness being treated in the eye. That's usually viral gene replacement, not always CRISPR, but the results can be life-changing. Duchenne muscular dystrophy, teams testing CRISPR to fix or skip broken parts of the dystrophin gene. It's the moonshot category, high need, active trials, not approved. So when you hear CRISPR cured X, ask two quick questions. Is there regulatory approval? Is it a one-time functional cure, or just symptom control? For now, the gold star answer belongs to sickle cell disease and transfusion-dependent beta thalassemia with Casgevy. The take-home, CRISPR has crossed from promise to practice, but only for a couple of diseases so far. The pipeline is loaded, the data are maturing, and the next couple of years will tell us which conditions graduate from trial to treatment. Genetic engineering cures are a reality. We should celebrate the wins without overhyping the work still to do. But the future expansion of curable diseases will be a great benefit for humanity.
The possibilities extend far beyond curing rare genetic disorders. Scientists could, in theory, edit genes to grant resistance to diseases like HIV, to lower the risk of developing heart disease or Alzheimer's. We could potentially modify genes to slow down the aging process, extending the human lifespan and health span. We could even target genes related to physical or cognitive traits, such as muscle mass, memory, intelligence. This is where the conversation moves from medicine to enhancement, from healing the sick to upgrading the healthy. This is the line that makes many people uneasy. This power comes with significant risks. The genome is complex. A single gene can influence many traits. Changing one gene to achieve a desired effect could have unforeseen and negative consequences elsewhere in the body. The power to rewrite our own biology forces us to ask profound ethical questions. Who gets to decide what constitutes an improvement versus a defect? Today, we might agree that curing a painful and fatal disease is a good thing. But what about editing genes to make a person taller, smarter, more athletic? Where do we draw the line? If these enhancements are expensive and available only to the wealthy, we risk creating a new and permanent form of social inequality. We could see the emergence of a genetically enhanced class and a natural class. There is also the critical distinction between editing the cells of an adult and editing the cells of an embryo. When we edit the somatic cells of a grown person, say their blood cells to cure sickle cell anemia, those changes affect only that individual. They are not passed on to their children. But if we edit the DNA of an embryo, or the reproductive cells, sperm, and eggs, we are making a change that will be inherited by all future generations. This is called germline editing. It means we would be altering the human gene pool itself. A mistake made here would not just harm one person, it would be passed down forever. This is a monumental responsibility. Are we wise enough to make such permanent decisions for the future of our species? Many scientists and ethicists argue that we are not. They call for a global moratorium on germline editing until we have a much deeper understanding of the science and have had a broad public conversation about the societal implications. The temptation to eliminate a terrible hereditary disease from a family line forever is powerful, but the risk of unintended consequences and the potential for misuse are equally daunting. Furthermore, the drive to perfect humanity could lead to a dangerous loss of diversity. Human genetic diversity is one of our greatest strengths as a species. If we define a narrow set of optimal genes, we risk a more uniform and more vulnerable species. What seems ideal today might be a liability in the face of an unknown future threat. We are moving beyond biology. This is the rise of transhumanism. The conversation about human enhancement is not limited to genetics. Another powerful idea is emerging: merging human biology with technology directly. This movement is known as transhumanism. Its core belief: use science and technology to overcome the fundamental limitations of the human condition, aging, disease, death, not as inevitabilities, but as technical problems. They dream of radically extending lifespans, enhancing intelligence, and transcending the frailties of our biological bodies. This might sound like science fiction, but early stages are real. Devices that restore hearing and sight, prosthetic limbs controlled by thought. The same principles could go beyond normal: eyes that see infrared, limbs stronger and faster than biological ones. The line between human and machine blurs. Imagine superhuman strength via exoskeletons, or a chip in your brain giving instant access to the internet, upgrades envisioned as the next logical step in human evolution.
Before getting the implant, you couldn't be alone without help for more than half an hour at a time. You obviously couldn't send an email or watch a movie or play online chess. I know you're a big fan of online chess. You couldn't do anything without help.
am.
And once you got the implant, you said it was like magic. So talk us through this technology. How do you use it on a daily basis?
Yeah, it's I like to say it's pretty simple. What I mean by that is, of course, the technology itself is not very simple, but how it's used is pretty intuitive. And I use it for all sorts of things.
Do you have
these
to turn
days.
it on? Like, do you turn it on?
I do. I do.
Okay.
So I have a little hat that has a charger in it. It plugs in, and I can command the implant to connect or disconnect at any point. And after that, I just do whatever I want on a computer. Whatever anyone else can do on a computer, I can do, and I use it for all sorts of things.
Do you have
Not
to
just
say
playing.
something in particular when you say you command, the computer to do something? Do you say cursor move or?
Yeah, just in order to connect, I'll say implant connect, and it'll connect.
And then after that, you just think a thought and it happens on the computer in front of you.
Yes, ma'am. That's basically how it works. Point.
Neuralink is constantly updating your software, making things faster, making things smarter. Have you noticed the technology changing and improving in the last year?
Yeah, absolutely. I think a lot of the user interface has changed. I think a lot of how they are calibrating, how they are reading the signals, they've constantly been updating things. So from where we were at the beginning, it is massive improvements. And the more people that join the study, the better it's going to get. I honestly don't know what it's going to look like when it gets, completely released, but I know it's going to be leaps and bounds better.
We've always used tools, from the first stone axe to the modern smartphone. Merging with our tools is a more intimate continuation. But what does it mean to be human if parts of our bodies and minds are manufactured? If memories live on external drives, are they still ours? As with genetics, inequality looms. Expensive enhancements could split society between the enhanced and the unenhanced. The pursuit of a post-human future requires deep thought about what aspects of our humanity we value most and what we are willing to change. Perhaps the most dramatic frontier lies in the brain, our consciousness, our creativity, our sense of self. The idea of a brain-computer interface is both tantalizing and terrifying. The initial applications are medical, helping people who are paralyzed to control robotic arms and to communicate by thinking. These devices read neural signals and translate them into commands. The next step: two-way communication, writing information back into the brain. Imagine feeding knowledge directly into your mind, learning languages and complex skills in a fraction of the time. Augmenting memory for perfect recall. This could fundamentally change education, work, and our personal relationships. AI integrated directly with our biology, a path that could lead to a hive mind or collective consciousness, sharing thoughts, emotions, experiences. But where would your mind end and another's begin? Who would control the network? The potential for manipulation and control would be immense. Thinking is not just logic, it's intertwined with emotions, bodies, and lived experience. If we offload cognition to machines or augment our brains with hardware, how will our consciousness change? Will we lose creativity, intuition, serendipity, virtual reality, and consciousness? Beyond changing our bodies and minds, technology is poised to change our experience of reality. VR fully immerses us in digital worlds. AR overlays information onto the real one. Today, entertainment, training, specialized work, but potential far greater. Imagine spending much of your day in a virtual world as rich and convincing as the physical one, to socialize, work, learn, play. For people isolated by geography or disability, this could be a profound gift, connection and experiences otherwise impossible. But if virtual life becomes more compelling than the real, it could weaken our social fabric, our connection to communities and planet. We must find balance. The idea of artificial consciousness looms. Many believe a truly sentient AI may be possible, an entity with subjective experience, feelings, a sense of self. Such a creation would upend ethics. Would it have rights? Would turning it off be moral? Our frameworks would be tested, and we'd be forced to ask what consciousness is: computation alone or something more? We stand at a unique moment in the 4 billion-year story of life on Earth. For the first time, a species can consciously guide its own evolution. The slow work of natural selection meets the fast, powerful hand of technology. Genetic engineering, brain-computer interfaces, artificial intelligence. These are developing realities shaping our children's lives, offering a chance to reduce suffering and unlock human potential. But they bring a heavy burden. Our choices now will echo for generations. We face critical decisions: heal and unite, or enhance and divide. These are not questions for scientists alone. We must foster a global conversation, educate ourselves and others, demand transparency, and establish thoughtful, equitable safeguards. The future isn't something that just happens to us. Choose to be conscious architects. Use our ingenuity to be more compassionate and connected. The cosmos brought us this far. The next step is up to us. Let us take it with care.
If you like these subjects, please like, share, and subscribe.